Hello, everyone. Today we will talk about testing a claim about two different means. Right. So let's start with some definitions. So two samples are independent if the sample values from one population are not related to or somehow naturally paired or matched with the sample values from the other populations. Two samples are dependent if the sample values are somehow matched, where the matching is based on some inherent relationship such as before or after data. Right. So some examples between the two. Independent samples for height of men and women. If we say data set 1 is body data and it includes the following heights of sample men and women, and the two samples are not matched according to some inherent relationship, they are two independent samples that just happen to listed in the same way, and this might cause us to incorrectly think they are matched. So we have heights of men, heights of women, two different samples. They have no relation to each other, even though they're measured in the same way. Dependent samples, students of the author collected data consisting of heights of husbands and their wives. 5 of those pairs of heights are listed below. So here there's a relationship. Each husband is matched with their wife, and these two data values have a relationship because the wife is paired with the husband. Okay? So first one, just random men and women taking a sample, that's independent. But if a couple is grouped together, then there's some inherent relationship. So I can't say that those are independent. So that makes it dependent. So a lot of times we think of independent samples as just no relationship between the two samples. And in today's lesson, what we want to do is see if we can find relationships between two means. And we do that through hypothesis tests. So we're going to conduct a hypothesis test of a claim about two independent population means, and we can construct a confidence interval to estimate the difference between the two independent population means. Okay, for population 1, we're just going to label everything we know already with a subscript of 1. For population 2, we do the same thing with a subscript of 2. So nothing really new there. The requirements, however, are a little stricter here. So requirement 1, the values of sigma 1 and sigma 2 are unknown, and we do not assume that they are equal. The two samples have to be independent, both samples have to be simple random, and either or both of these conditions have to be satisfied. That is our normal. N1 and N2 are greater than 30, so if they're both large sample sizes, or both come from populations where the data is normally distributed. So if our requirements are all set, we have this new equation for t-test to find our t-value. So it's virtually the same as before, but we're factoring in two means here. So we're subtracting the sample means, subtracting the population means, and then in the denominator, we're squaring the standard deviations, dividing by the number, and adding those together, and then we square root them. So a little bit harder of a computation here, but we're just going to typically plug this in to a calculator. But a lot of times also here, it's important to note, a lot of times we're using the same value here, so that's 0. So sometimes people don't even write that. So you might see the formula is just x bar 1 minus x bar 2. So don't get confused, it's the same thing. Our null is often, or is going to be that the means are equal. So if the means are equal, that makes 0. Right. We have to be a little careful here with degrees of freedom. So when finding critical values or p-values, use the following to determine the number of degrees of freedom. So although these two methods typically result in different numbers of degrees of freedom, the conclusion of a hypothesis test is rarely affected. 1 is you just find the degrees of freedom by both and just use the smaller number. I typically do that way. Just find the degrees of freedom of both, take the smaller number. The other way that's more accurate, but shouldn't really matter, is if we use this formula over here. We'll just stick with the conservative estimate. Just take the smaller degrees of freedom from the two numbers. And then p-values are automatically provided using technology. If technology is not available, refer to the t-distribution. And then critical values, always use our t-distribution table. Okay, let's look at an example. So listed below are heights of randomly selected U.S. Army male personnel measured in 1988 and different heights of randomly selected U.S. Army male personnel measured in 2012. Use a 0.05 significance level to test the claim that the mean height of 1988 population is less than the mean height of the 2012 population. Okay. So these numbers look big, but be careful our unit. We have millimeters here. All right. So all four of our requirements are going to be satisfied. I'll give you that the data is normal. Nothing to suggest it's not a simple random sample. These are independent, took place at different times. We're not measuring the same height, the same people, so they're independent. So we're all set here. All four of those requirements that we talked about are going to be met. So step one, the claim that the men's height of the 1988 population is less than the mean height of the 2012 population can be expressed as mu1 is less than mu2. Step two, if the original claim is false, the other claim would be mu1 is greater than or equal to mu2. So we choose the alternate hypothesis still without equality. So our alternate hypothesis is the first mean is less than the second mean, and then our null hypothesis will, instead of it equals that number, we just assume the means are equal. So this is pretty standard. It will always, for the null, be the means are equal. The alternate will be less than, greater than, or not equal. So now we have this assumption, since the null is mu1 is equal to mu2, that's 0 when we subtract them. So when we go back to our formula, we're assuming that's 0, so we don't really worry about plugging in those values. Critical level, still 0.05. Right. So let's continue working. Steps 5 and 6, we can skip them when we use technology. If we were to plug these two data sets in, which you can do using SPSS, and we can check it without technology if we have our t-distribution table. But we're going to rely on technology here. So I gave it to you to look at in the corner here. So with technology here, but we'll also look at without. So we're going to use this t-distribution. We have to use a t-distribution when we're testing two means. It will always be a t-distribution for this class. Okay. And we have our values. For 1988, n is 12, x bar is 1739, standard deviation is 66.6012. So this is going to be our x bar 1. We're assuming this is 0, and this is our standard deviation 1 and our n1. Right? And then we have n is 15, x bar, and s. This will represent S2, N2, and X2. Okay. So we plug all of those numbers in, and we get our t-value. Our t-value would be negative 1.679, which, like I said, you could skip this step if you plug the data set into technology. It'll give you that value. And it gives you the critical value and the p-value, which is really nice. So if you want to compare it to the critical value or the p-value, we're going to get the same thing. And then degrees of freedom, if we use technology, is 19.30. So if we use the method I stated before, you just take the smaller degrees of freedom, which would be 11. 12 minus 1 is 11. That's smaller than 15 minus 1. So if you use degrees of freedom of 11, you should still get the same answer. The numbers are going to be different, but you should still get the same answer. It is always more accurate if you use technology to do it, but 99.9% of the time you'll get the same answer just by doing n minus 1 of the smaller n. But if you have technology, use the number they give you. And it will also compute a confidence interval for us as well. So I have StatDisk up here, but SPSS does the same thing, and we'll look at that in our lab, how to find all these values. Right. So when I wrote the solution, I said the degrees of freedom is 11, so that's that first method. Just take the degrees of freedom of the smaller sample. The p-value is greater than 0.05, barely, it's 0.0546. Because the p-value is greater than the significant level, we fail to reject. We also see if we looked at the critical value of negative 1.72, it would just miss that range as well. So minus 1.679 is slightly bigger than that critical value. So if we look at our bell curve, if we have our critical value here of negative 1.72, 1.6, would fall just outside of that critical region. So this is our critical region, and negative 1.679 would fall just outside of that region. But it's a little easier here to see with the p-value. This p-value is greater than 0.05. So since with technology, p-value is much easier, so we can just compare it to the significant level. And because the p-value is greater, we fail to reject the null. When we fail to reject the null, that's when we say there is not sufficient evidence to support the claim. Then we plug in the claim that the mean height of 1988 male population is less than the mean height of the 2012 male population. Right. Here's another nicer drawn picture than the one I drew of if we use the critical value method. Our test statistic here is outside of our critical region because negative 1.679 is slightly bigger than negative 1.727. So it does this here, would not fall in the critical region. All right. Next time, we are going to talk about what's called ANOVA. Have a great day, everyone.